Okay, so the end of chapter 14, the ethers and epoxides chapter deals with epoxides. Now, to be honest with you, epoxides should be relatively straightforward at this point because we've done reactions last semester of epoxides that were acid catalyzed ring openings. And this semester we've done base catalyzed ring openings with the Grignards and the H- and the C triple bond C minus. So what I'm going to do is just go back and kind of review why we get the regioselectivity that we do, and then we'll finish up with starting into um, chapter 14 or 15 actually, starting into chapter 15 dealing with the outdienes, which is our next topic. So as far as epoxides go, what we hopefully remember from last semester is the idea that with an epoxide, when you add a nucleophile to the epoxide, you're always going to get the nucleophile and the resulting OH group, and that will always yield the trans stereoselectivity. And that's always going to occur because we have this triangular intermediate compound in essence, and so the nucleophile has to attack underneath, and then depending on which carbon it reacts with, we would then break the carbon-oxygen bond. That will then give us an alkoxide or not. So we'll either get an O minus or an OH, and that'll lead to the final product. And we'll talk about the two modes here, refresh ourselves on the two modes here now. But the idea is that it always gives the trans stereoselectivity because it's a triangular compound. Now last semester we talked about the idea of acid catalyzed ring opening. And so what we said was, okay, if I take an epoxide, let's say like this, and I'm going to treat it with H+, the first step is I'm going to protonate that ether, even though it's a cyclic ether, and that's going to give me an oxonium ion. And what happens here is we draw the intermediate more like it was a bromonium ion because the oxygen isn't particularly happy with the plus charge. So what I'm going to do is I can almost envision this intermediate sort of looking like this in terms of it having then partial bonds to each of the oxygens, and then these two carbons sharing in the positive charge. So I'm going to actually, in essence, transfer the positive charge from the oxygen to these two carbons, which are better able to handle it simply because they're less electronegative than oxygen. So again, if you add acid to the epoxide first, you're going to get the formation of this type of intermediate. Now, I'm going to rewrite that intermediate over here, but the issue is, so if I have this type of oxonium ion intermediate, what happens when the nucleophile then, and in this case, it's going to be whether it's a neutral nucleophile like water or alcohol, or it could be, after the protonation here, it could be a Br minus or a Cl minus. Where do these nucleophiles then attack? Do they add to carbon A or do they add to carbon B? And in this case, because I've protonated the oxonium ion, these are going to add to the carbon with the most delta positive charge. And that's going to give them a mechanism that is in quotes SN1 like. So which of these two carbons, A or B, has the greatest delta positive charge? Well, it's going to depend on how many alkyl groups are attached to each of the carbon. If I was to make carbon A of pure carbocation, it would look like this. So in other words, if I broke this carbon-oxygen bond, I would get this carbocation. That's if I was to look at carbon A. If I was to break this carbon-oxygen bond and write it as a pure carbocation, it would look like this. Now, which of these two carbocations is more stable? Well, clearly the secondary carbocation is more stable because we don't write the structure of primary ones. So when we come back over to this molecule in the triangular intermediate, this carbon will have the greater delta positive charge because, in quotes, it looks more like a secondary carbocation, and this carbon over here looks more like a primary carbocation. And so when we protonate the ring, the nucleophile then adds to the carbon that is most substituted. Okay? There's no issue of steric hindrance because we've changed the mechanism to make it look SN1-like. Now, if you're curious to say, well, why don't we write like this intermediate or this intermediate? Why do we write the intermediate showing the oxygen attached to both carbons? It's really easy to prove that this is the case because remember, the nucleophile would have to add underneath so that we would get a trans stereochemistry. If this intermediate was to form, we would get a 50-50 mixture of cis and trans. So it turns out that the intermediate looks more, well, the intermediate doesn't look more, it is this type of a structure. But we know from the regiochemistry that under acidic ring cleavage, the nucleophile, whether it's weak or has a negative charge, will always add to the carbon with the most substituents. So that leads us to a bunch of different possibilities. I could say, okay, what's this molecule going to give when I react H plus and H2O with it? Well, it's going to open up the epoxide, so I'm going to end up with the two OHs added. If you're not sure of the mechanism of this, we would take the oxygen and protonate it with the H plus. That would form our protonated oxonium ion with the plus charge on the oxygen that would then, in essence, transfer the positive charge to the carbon. So we'd have a delta plus here, partial bond to the OH, partial bond to the CH2, and we'd have a delta plus charge here. And then our water molecule would come in and it would add to the carbon with the most substituents, and then it would break that bond so that we would end up forming a CH3 with a CH with the oxonium ion now down here and a CH2OH there. Then we would lose our H plus, regenerate the catalyst, and that's how we get our final product of having an OH here and an OH there. So when we use H plus H2O, we are acid catalyzed ring opening to form the, in essence, trans glycol here. We could do this with H plus H2O or H plus and an alcohol. And that would allow us to put an OR group on one carbon to form an ether and the OH to form the alcohol on the other. Now the HBr and the HCl mechanisms I didn't talk about when we talked about acid catalyzed ring opening, but you can imagine that they would be the same. If I added HBr to this, what product would I get? Well, I would add the Br to the most substituted carbon, and then the OH would swing over to form on the least substituted carbon. You could go through the mechanism of this by protonating the oxygen and then putting the delta positive charges down on these two carbons and then adding the Br minus underneath to form this product. The same thing would be true for HCl. So whenever we have an acid and a nucleophile, we acid catalyze ring open so that the nucleophile attacks the carbon that is most substituted. Okay, and we talked about that last semester. Base catalyzed ring opening is something that we just did recently. And base catalyzed is kind of a misnomer because it's really not base catalyzed. There's no catalyst here. Let's see, I should probably erase here to... So base catalyzed, again, there's no catalyst here, so the base is just going to attack the nucleophile, is going to attack the epoxide and then open it up. If we go back to our same epoxide that I just used, and now I'm going to react it with a negatively charged nucleophile, now this mechanism is going to go with a much more SN2 characteristic. And what I mean by SN2 here is that it's going to go with the steric hindrance being playing an important role. So in this case, if it's SN2, I have a secondary position versus a primary position. Now the nucleophile is going to come in, attack the least substituted position, the one that's least sterically hindered, break this carbon-oxygen bond and give that pair of electrons to the oxygen. That means in this case I'm going to form an O- with my nucleophile, and then in a second step I'm going to add H plus H2O to then protonate that alkoxide to give me the final product. So by doing this with a strong negatively charged nucleophile, but the key is not protonating the epoxide, I now change the mechanism to be steric, to be SN2, where now steric hindrance plays a huge role. So in essence, what I've done is I've reversed the regioselectivity of this reaction. Now, if I took this epoxide and I treated this with hydroxide, and then after that added H plus H2O, I would still have opened up the epoxide to form the OH and the OH. So we don't see a regioselective difference if we use hydroxide to open up this epoxide to form now, again, still our trans diol. I can't tell the difference between these two oxygens. So we get the same product whether we use acidic or basic ring opening when we use hydroxide or H plus H2O to form the trans glycol or the trans 1,2 diol. But where we would see a difference in regioselectivity is, let's say I wanted to add the bromine in an opposite regioselectivity as I do in this reaction. So here I added the Br to the most substituted carbon. and ended up with the OH on the least substituted carbon. Could I now reverse that by using Br minus? And the answer is yeah. If I took that same epoxide and I now added Br minus to this, the Br minus would attack there, pair of electrons would move that way. I would now have my O minus with my bromine there, and again I'd have to come back later and add the then H plus H2O step to then protonate that alkoxide ion into the alcohol. But notice that now what I've done is I've reversed the regioselectivity, so now the bromine is attached to the carbon that is least substituted, and the OH is attached to the carbon that is most substituted. This is exactly the opposite of what I got using HBr. So what it allows me to do is it allows me to add the bromine to either carbon depending upon what product I want to form. Okay. Now, we could do the same thing with HCl. We could add HCl one way, Cl minus the other. We've just been through opening up the epoxides with either R minus or H minus. And unfortunately, there's no stereochemical way, or not stereochemical, regioselective way to add the R to the most substituted carbon here, simply because in this case the R minus and the H minus have no choice but to add to the carbon that is least sterically hindered. There's no acid catalyzed equivalent of these, because if I added acid, it would protonate the R minus and not the epoxide. So there's no two different ways to do this reaction and add the R minus to the more substituted carbon. That reaction doesn't exist. Okay, so that's kind of a review. And one new twist on doing ring opening of epoxides, but it now gives us the opportunity to form either product, particularly with the HBr or Br minus, because now I can form either product. Okay, so that's really the end of chapter 14. And now we're going to move into chapter 15, dealing with dienes. Now, we've already talked about alkenes, one double bond in the molecule. And so that we talked about how to make alkenes. We talked about the reactions of alkenes, what happens when you react HBr with this, H plus H2O, and a whole variety of other reactions. Now what I'm going to talk about are dienes, which means in my molecule I somehow have two double bonds. And there's two ways that you can have the double bonds oriented in a molecule. So a molecule that contains two double bonds can either be, and I'm going to start with the second one first here, an isolated diene, where there is more than one double bond in between the two double bonds. There could be one, there could be two, there could be three, there could be four. These are what are called isolated dienes. And so isolated dienes have exactly the same reactions as alkenes, except now there's two double bonds, so they can take twice as much stuff. So they react like normal alkenes. The special alkenes are what are called conjugated dienes. So if you had a double bond separated by one single bond, this is what's called a conjugated diene. And conjugated dienes are special. Their reactions are going to be slightly different than isolated dienes, and we'll get to those in the next lecture. And it turns out that these double bonds are more stable than isolated double bonds. And that's actually easily determined by doing hydrogenation reactions. So what people have done in the past is they've taken their diene, and I'm just going to kind of show that it could be conjugated or isolated. They react this with hydrogen and palladium, and they measure the delta H of this reaction to give them then their alkane. So this heat of hydrogenation is exothermic, so it's negative. And so when they take, for instance, this 1, 2, 3, 4, 5 membered isolated diene, and they were to react that with hydrogen, or take, and I'm going to add a carbon on here, 1, 2, 3, 4, 5 membered conjugated diene, what they find is that they get the same product in both of these reactions. So if I reacted this with H2 and palladium, I would get pentane. And if I reacted this with H2 and palladium, I would get pentane. So they get the same product, pentane. And then when they reacted the isolated diene, they got, I don't know, I'll just make up a number. And I am just making up a number. Let's say they got minus 100 kilocalories, kilojoules. They got minus 100 units. So that was with the isolated diene. Well, it turns out that when they did that same heat of hydrogenation with a conjugated diene, they ended up only getting, I don't know, let's just say for the sake of argument, minus 80. And you can look up the exact numbers in your textbook. So it turned out that the conjugated diene gave off less energy than the isolated one. And so what that means then is that means that the conjugated system turns out to be more stable than the non-conjugated or the isolated system. And so that's how we can experimentally determine that the conjugated diene is more stable than the isolated one. So somebody did this reaction and they figured out, okay, I have experimental evidence that the conjugated system is more stable than the isolated system. And so they would say, well, why is that? Why is that the case? And what it does is it has to do with what's called the overlap between the pi bonds in the conjugated system. So here's a conjugated system. First of all, this is the conjugated system for CH2 double bonded to CH with a single bond CH and then double bonded to CH2. All of these carbons are sp2 hybridized, which means that this is the structure, and what you have is you have all of these sp2 hybrid orbitals then have unhybridized p orbitals. And it turns out that all these p orbitals can be parallel to each other. Now they have to be parallel if I'm going to form the first double bond, and then I'm going to form the second double bond. Okay, and so this diagram here kind of shows the orbital picture of this, what's called butadiene molecule. Now it's these carbons 2 and 3 though, they're next to each other. They have a single bond, but they have p orbitals that are parallel to each other. And so it turns out that the reason why a conjugated system is more stable is because there's a little bit of an overlap between these two carbons, between carbons 2 and 3, because their p orbitals are parallel to each other. Now, bond distances are characteristic of single, double, and triple bonds. Carbon-carbon single bonds are the longest. Carbon-carbon double bonds are a little bit shorter. And so it turns out that this bond is a little bit shorter than a single bond. Not a lot shorter, but a little bit. And so that's indication that we do have this partial overlap, which means this single bond has a little bit of double bond character. And so that stabilizes the molecule because of this partial overlap. If we looked at kind of the picture of the electrons, what we see is that we have the negative charge here of the electron of these clouds. They're kind of smeared over all four molecules. So it's this partial overlap that stabilizes conjugate dienes. And actually, this has been in textbooks for years, and it was only within, I'm going to say, the last 5 years that there's been some really good experimental evidence that this bond is actually shorter than a carbon-carbon single bond. And it turns out that one of the people who did that research is a chemistry professor at Oberlin. And so he was able to use infrared spectroscopy, very specific and very complicated infrared spectroscopy, to show that this bond was actually shortened, and provide what probably was the first experimental evidence that this partial overlap stabilized the double bond. Before, everybody just had kind of assumed that to be the case. Now, they didn't assume that the conjugated was more stable than the non-conjugated, because they had experimental evidence of that. Okay, so that's going to set the stage for talking about reactions of conjugated dienes in the next lecture. And where we're going with this, just for a moment, is that we're going to create here the ultimate conjugated system eventually. One where we've got alternating single bonds and double bonds in a six-membered ring. And so we need to talk about conjugated dienes and their reactions in order to understand then the chemistry of benzene and of anything that has an aromatic ring, because an aromatic ring is the ultimate conjugated system of single bond, double bond, single bond, all the way throughout that six-membered ring. So that's ultimately where we're going after chapter 15. We'll then be able to get into benzene and aromatic chemistry in chapter 16. Okay, so most of this is actually kind of a review dealing with the acid and base ring opening of epoxides. And so that's going to be what the online quiz is going to be about, matching up the products of acid and base catalyzed ring openings, and maybe a word problem about conjugated dienes. But we're going to get much more into conjugated dienes in the next lecture period.